Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, in this module we are discussing the risk assessment and the reliability of the space assets. So, in the last session we discussed that is the system reliability of a system which consists of out of k elements, n elements are necessary for the operation of the system. Then we consider the dynamic redundant systems. In dynamic the dynamic redundant system is different from the static system. In static systems all the units are connected, means it is powered, whereas when we consider dynamic redundant subsystems we use the switches to connect it to the, when the main system fails, then the redundant system will be connected to the input and output through switches. There can be one switch at the input, it can be single pole double throw or only one single pole single throw. We will show you this. So, these are the topic we discussed and in the last class, and we have seen that is the system reliability we are able to find it from the binomial distribution function. Okay. Then the assumptions we took, that is each element works independently, each component has the same reliability. So, this simplification we took. Then we consider a very simple example which consists of two elements, and we found the reliability considering both the elements are performing. Then the next case we consider the first one fails, the second one performs, and the third is the first one is performing and the second one has failed. And we found out the system reliability is given by this expression, and we finally wrote this expression like 2 is 2 r minus r square, and considering that is the failure rate as constant failure rate. So, in fact, when the failure rate is constant, then you can write the reliability minus lambda t, where this is the hazard rate or the failure rate. Okay. So, using this we are able to find this, and once I have the reliability function, then we can calculate the failure rate of the system by using this expression. This is f t is the probability density function of failure divided by the, that is the reliability function, and this is the way we did, and finally we got this is the expression we derived. And as I said, now the failure rate is no more constant, but it is a function of time. Then we consider that is the dynamic redundancy with switching. So, what I was telling at the beginning. So, if you see, this is a single pole double throw switch. So, whenever the main, this is the active or the main system, this is active and this is redundant. So, whenever the active one is performing, then this both the switches will be connected to this pole or this port, it will be connected to this port. Okay. And whenever there is a failure of the main system, it will be going to, it will operate, this switch will come down and it will be connected to this port, and finally similarly the output switch also. The second case, it is the input section, there is no switches, but at the output it is a single pole single throw switches. So that whenever this, you can consider like a circuit, suppose the main or active one fails, so this becomes open circuited. So, that time the switch will go there and then this will start, the redundant one will start performing. Okay. So, this is the principle, and we derived the system reliability considering this, one is active, that is the primary, and one is standby, that is the backup, and we discussed the switching mechanism is perfect here, means the switching mechanism is perfect. What does it mean? That it always works without failure. So, in my last lecture I wrote with failure, it should be without. So, just you note down this correction, this is without failure. So, this reliability function S switch is equal to 1. In subsequent lectures, we will consider if that is less than 1 also, and we will see how the system behaves whenever the switches which are also having some reliability figure, there is some probability of failure is there. Then we calculate the failure times of the components, and we use the Poisson's distribution. So, this is the expression, and then we considered t is the mission time, that means we are considering a time t where the main system is still working. So, the failure follows a Poisson distribution of rate, the failure rate as lambda. So, the probability that the component survives at time t, so this is given by this one. Okay. And the primary unit works without failure until time. So, that will be given by this one, and this we wrote as P 1 t. We will now go proceed further. So, we will assume that the point that is the primary, fails at time tau, and the backup unit it survives means there is no malfunction in the backup unit. So, it survives for the backup survives for the remaining time, so t minus tau. So, if that is the case, so we will consider this, and then we will consider, that is the failure of the primary, primary unit which occurs at, already we said, which occurs at tau, and what is tau? Tau will belong to, that means it should be a subset, it can be from any time 0 to t. So, t is the mission time. So, any time in between the mission time. So, it is 0 is the starting and t is the end of the mission life. So, so tau is it belongs to this set 0 to t. Okay. Now, the probability that the probability that the primary fails at time tau then I have the probability function. So, if I differentiate the probability function, I will get the probability density function. So, that probability I can find d by dt of e to the minus lambda t multiplied by d of tau. So, we are considering just a small time interval delta tau around the tau, and we are using t is equal to tau. So, this will be equal to lambda e to the minus lambda tau d tau. Now, the probability that the probability that the backup survives, probability that the backup element survives from tau to t, tau. So, the failure has occurred at time t. So, backup unit must work from tau to t. So, that probability is e to the power minus lambda t minus tau. So, now the contribution of the system reliability. So, the contribution to the system reliability from the failure at time t, at time tau, is, we can write. So, we will write this as P 2 is equal to integration 0 to t, then lambda e to the power minus lambda tau multiplied by e to the power minus lambda into t minus tau d of tau. So, if we perform this integration, we will get, so this is equal to 0 to t lambda, then e to the power minus lambda t dt. So, this term and this inside this term will cancel each other. So, I can write it lambda e to the power minus lambda t into dt and d tau, actually it should be d tau, not dt, it is d tau. So, if you do the integration, you will get lambda multiplied by t, then e to the power minus lambda t. Okay. So, the total system reliability is So, total system reliability R s will be equal to P 1 plus P 2. Already we have derived the expression for P 1, now we have derived the expression for P 2. So, as I said, R of S, that is the system reliability, T is equal to P 1 plus P 2, and already we have seen P 1 is equal to e to the power minus lambda t, and P 2 is lambda t e to the power minus lambda t. So, this I can write as 1 plus lambda t e to the power minus lambda t. So, this I can write an expression like this, k is equal to 0 to 1, then lambda t to the power k by k, and then e to the power minus lambda t. So, this is what? This is actually the Poisson distribution. or it is Poisson random process. So, now we can write a general formula where we are having some n elements and you need m elements to perform. So, now we will go for a generalized expression for the system reliability with dynamic redundancy. So, generalized means we will consider some variable m or n or I or k to represent the total number of elements and the minimum number of elements which are required for the operation of the system. So, let us consider a system which is constituted in the reliability sense of m normally active elements in parallel, where n elements can in turn be placed in parallel to replace a failed main element. Okay. So, here we will consider the failure rate, this one, the failure rate lambda I of each of the elements is constant. So, as already you have taken in the previous cases also, we will consider the individual element has the constant failure rate. The reliability R of the system for m elements in a correct operation state is given by Poisson's distribution, that already we have seen in our previous slide. So, now we have seen for we have taken for just for 2, and we have said that out of T 1 element must work satisfactorily and how the backup element will come, and we derived the expression for one main unit and one backup unit. Now, if you say this is m and n, then that expression will be, it will be just it is an we are taking these other terms. So, we have used our previous slides. So, I wanted to show you the previous slide anyway. So, this one it is represented. So, now here our total number of this is the m you need this active elements in parallel, okay, where the n elements can be turned. So, now this is the generalized expression. Now, once you have this reliability function, you can find the mean time to failure. So, what is mean time to failure? Mean time to failure is this is the integration of T f t. So, T f t dt, and if you integrate it from 0 to infinity, you get the MTTF. So, how I get f t? F t I will get by differentiating this a negative differentiation of R t, that is f t will be equal to minus R t by d of R t by dt. So, you can find the mean time to failure like this. Now, you see this is a very simplified assumption we have taken, that is whether it is a backup element and the main element having the same failure rate. But if we want to generalize it the more, that is considering the different failure rates. So, in that case deriving an expression, it can be very complex or it may not be possible. So, we will consider few some few particular examples. So, first we will consider the redundancy with different failure rates which depend on the operational state. Then a second case we will consider the equipment redundancy taking into account the reliability of the switching element. Now, whatever you have done in this in the previous the examples, there we considered this, the reliability of the switch is 1, means it will not fail. But now we will consider in this second example where there is the finite the probability is not 1, it can be anything between 0 and 1. Then we will consider that is the redundancy of the travelling wave tubes, that is the TW tubes in the channelized part of the FFL, that also as an example we will take. So, let us now consider the first case, that is the redundancy with the different failure rates which depend on the operational state. Now, the considered system, it consists of a principal element and a backup element which can replace it. Okay. Now, we will consider the failure rate of the principal element is lambda p, and the failure rate of the backup element is lambda r when the element is inactive, and lambda s when the system is when the backup system is operating. So, these are the three cases we have considered. For the principal element it is lambda p, that is the failure rate, and the failure rate of the backup elements under two cases. One case when it is inactive, means when the main unit is operating or the primary unit is working, and then the backup unit the failure that it still can fail, that is given by lambda r. And after the main unit has failed and the backup element has started operating, in that case we are considering lambda s is the failure rate. Now, we will evaluate the reliability of the subsystem by considering the various probabilities of failure and correct operation. Okay. So, consider a system, it consists of a, as we said, this is the principal element with the failure rate is equal to lambda p, then a backup element which replaces it, failure rate of the backup element is lambda r when the element is inactive, and lambda s when it is operating. So, we can now write the reliability of the subsystem, or we can evaluate the reliability of the subsystem in considering the various probabilities of failure and correct operation. Okay. So, probability of correct operation of the principal element between 0 to t is given by this, because already we know it is given by this expression. Secondly, the probability of the failure of the principal element at time t f. So, now this this Poisson that distribution will come here, because we are considering at time tau. So, this system has worked from 0 to at t f. So, at time t f, when t f is less than t, t is our mission time. So, that is given by lambda p e to the power minus lambda p into t. Now, the probability that the backup element being in good order between 0 to t f. So, that means when it was inactive, so that will be given by this expression. So, this already we have got from this, because since the lambda r is constant. So, these are the three cases. Now, the fourth case will come, the probability of correct operation of the backup element between t f and t time t, means now the main element has failed at the time t f, and now the backup element has been switched on. Now, the backup element should work satisfactorily, there should not be any failure from t f to t, then the mission is successful. So, this is given by e to the power lambda r t minus t f. Now, the correct operation of the system at time t, so it is ensured, that is the system is working or not, it is ensured if the principal element is operating at time t, we having the reliability R p, or so this is one condition. What is the other condition? So, first what we are considering, that the main system or the primary element, it will not fail from time 0 to t, where t is the mission time. Okay. What can be the other way? The other way can be after failure of the principal element at t f, the backup element is operating at time t. Okay. So, then it is given by the reliability R s. Here again, what is the condition, that element should be, its health should be, it should not be a failed element. Over the time a element can fail, so that should not be there. So, we will consider both all those probability functions. So, for the backup element to be in good order at time t, it must operate correctly between time 0 to t f and between t f to t. What does it mean? That you have a main unit and a redundant unit. Now, the redundant unit also can fail during a storage time, okay, when it is inactive. So, what is the condition? That it should be in a good condition whenever that switching to the, when the main system has failed and the redundant system is going to start. So, if I consider all these cases, then I can write the reliability, system reliability is equal to R p plus R s. So, R p is given by. So, what does it mean? That my system has worked throughout, there is no failure of the main unit. Now, we will consider the second case. The second case is, what is this lambda p? So, this is, it has failed at T f. The system, the main unit has failed at time T f, and what is this? This is the probability that this backup unit is in a good condition when it is switching over to act or to replace the main unit. And what is this term? This term represents that the backup units will work without fail till from T f to T. Okay. So, now what you have to do? You have to do some algebraic operation and we get the final expression this. Now, this is the system reliability function considering the different failure rates of the main unit, failure rates of the backup unit again under two cases. One case, it is while storage or while in inactive condition it should not fail, and the second case is it should perform satisfactorily from the time from the main unit has failed till the time the mission time t. So, you can further simplify this and you can get this expression, and now we can find the system reliability. So, I can add this the first term and I get this is the total system reliability, and then I can calculate the mean time to failure. Mean time to failure we can calculate, as I already said, once I am having the reliability function I can find the probability density function of failure f t, and once I find f t I can calculate the mean time to failure just by integrating t into f t from 0 to infinity. So, if you do that you will find the mean time to failure is given by this expression. So, where what are the TP, TR and TS are the mean time to failures of the principal equipment, the backup equipment when inactive and the backup element when it is operating respectively. So, let us take a particular case. So, let us consider a system having the same failure rate that is the lambda p for the operational units and a 0 failure rate for the inactive units. Then the expression becomes like this, and this expression already we have found out using this previous cases. We have when we started we derived this expression. So, I will conclude here and we will continue with this topic. Thank you very much.